Hey there, we're going to look at 4.4 today on graphing polynomial functions. We're actually going to split this into two lessons. So we're going to do 4.4 part A today, and we'll do 4.4 part B tomorrow. And so we'll look at the first two examples today, and then we'll look at the second objective, which is identifying general shapes tomorrow. But the objective of what we're going to look at in this lesson today is to be evaluating polynomial functions. And that comes from standard APR3, being able to graph them and identify zeros and dealing with end behavior. So again, a lot of the standard goes towards the second part of this, but evaluating polynomial functions is the foundation of what we need to be able to graph polynomials later on. All right, so we're going to look at a couple definitions here first. A polynomial is any expression written in the form this. Now, this form looks kind of crazy, but basically all we're talking about here is like having like 5x to the fifth minus 7x to the fourth plus 3x cubed, because a sub n is just some number n, and then the power of n is like the power of 5 here. And then n minus 1 would be, well, 5 minus 1 is 4. And then we can keep going down the chain all the way down to squared first, and then finally a constant at the end. And you'll see the stipulations here that a sub n cannot be 0, so my leading coefficient can't be 0. And then all the rest are real numbers, and of course all the n's, or the single n, is a whole number. So the standard form of the polynomial is when all the values of the exponents are in descending order. So if we look at this again, so we look at the powers 5, 4, 3, plus x minus 9, right? So all my powers are in descending order because I go from 5 to 4 to 3. There's no second power, there's a first, and there's my constant. Another definition to know is the leading coefficient. The leading coefficient is the first term of a polynomial that is written in standard form. So again, being in descending order. And so looking at the example we have here, the leading coefficient, this would be 5, because that is the highest agreed term, right? X to the fifth. And the coefficient of that is 5. And again, it could be positive, could be negative, could be a fraction, could be whatever. It's just whatever the value is. If my leading term was just like x to the eighth, then remember there's a 1 in front of that x to the eighth. And so let's look at a couple examples of doing degrees and leading coefficients and writing these in standard form. And so state the degree and leading coefficient of 7z cubed minus 4z squared plus z. And if it's not a polynomial of one variable, explain why. And so this one, first off, we do have all z's. There's no other variable involved. So this is a polynomial of one variable. And so the degree of this is what? Well, it's third degree, and remember we talked about these terms in section 3. This is a cubic polynomial. Well, what's now the leading coefficient? Well, the leading coefficient, remember we need to be in standard form, so third degree, second degree, first degree, so we're in standard form. The leading coefficient is 7, okay? As we look at example B here, 6a to the third minus 4a squared plus ab squared. State the degree and leading coefficient. If it's not a polynomial of one variable, explain why. Well, let's look at our variables. We've got an a to the third, an a to the second, and then an ab squared. That's two different letters. So this is not a polynomial of one variable, because it contains both a's and b's. All right, so let's look at the next example here. 3x to the fifth plus 2x squared minus 4 minus 8x to the sixth. Again, stating the degree and the leading coefficient. And if it's not a polynomial in one variable, explain why. So take a second, look at this one and see what you think. All right, hope you paused the video there. So first off, this one's not in standard form, but it is of one variable, right? Because we got x, 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 and we have a constant. So putting this in standard form, we'll go from high to low. So I've got 6th degree first, so negative 8 to the 6th. I've got the 5th power next, so plus 3x to the 5th. Second is next, and so plus 2x squared. And finally, the minus 4. And so now we're in standard form. And so what is the degree of this polynomial? Well, again, it's the highest power. And so the highest power is 6. And so the degree of this polynomial would be the 6th degree. What's the leading coefficient? Well, remember, the leading coefficient is the one that is in front of the highest power, and so that would be the -8. All right, and so that's example 1. Let's go on and move to example 2. Evaluating polynomial functions here. We're going to look at a couple of word problems here. The volume of air in the lungs during a 5-second respiratory cycle can be modeled by this function here. We'll come back to that in a second, where V is the volume in liters and T is the time in seconds. This model is an example of a polynomial function. Find the volume of air in the lungs after 4 seconds into the respiratory cycle. And so we're going to take this 4 and understand what is it going to plug into. Is it the input, is it the time, or is it the output, the volume? Well, it's obviously time because it said 4 seconds. So we're going to do V of 4 is equal to negative 0.037 to the 4th power, or sorry, 4 to the 3rd power, plus 0.152 times 4 squared plus 0.173 times 4. And so we will do all the order of operations here. We'll cube this, we'll square this, and so we get negative 0.037 times 64, 0.152 times the 16, and 0.173 times the 4. And so combining all that together, we're going to get that V of 4 is equal to negative 2.368 plus 2.432 plus 0.692, and adding all those together, we're going to get 0.756. Now, what does that mean? So take it back. 4 is the 4 seconds in the respiratory cycle. The 0.756 is the volume in liters that is in the lungs. So after 4 seconds, there is 0.756 liters of air in the lungs. That's what it means. All right, so let's look at example B. Height of a toy rocket during a 2.35 second flight is predicted by the function h of t is equal to negative 4t cubed plus 6t squared plus 8t, where h is the height in meters and t is the time in seconds. This model is an example of a polynomial function. Find the height of the toy rocket 1.25 seconds into the flight. And so again, with this problem, we're going to do what we did in the previous. We're going to take the 1.25 and plug it in for the t because we're dealing with the time and we're looking for the height. This 2.35 seconds is only important because we're talking about what this rocket's going to do. It's going to come up, it's going to go back down. So the point at which it hits the ground is 2.35 seconds. And so h of 1.25 is equal to negative 4 times 1.25 to the 3rd, plus 6 times 1.25 to the 2nd, plus 8 times the 1.25. And so again, we will deal with our powers here. So h of 1.25 is equal to negative 4. 0.125 to the 3rd power is 1.953125. We'll keep all this there for a moment. We'll deal with them later. 125 to the 2nd is 1.5625, and then plus the 8 times the 1.25, and we'll do all the multiplication on the next line. And so h of 1.25 is equal to negative 7.8125 plus 9.375 plus 10, and adding all those together, we get 11.5625. And so again, relating this back to our problem, so after how long? It was 1.25 seconds. The rocket will be at a height of 11.5625, and the units are in meters. All right, and so we're going to look at just a couple more examples real quick. Looking at example 3, dealing with the function of with the variables. And so find b of 2x minus 1 minus 3b of x if b of m is equal to 2m squared plus m minus 1. And so what this means is we're actually doing two separate functions in the same problem. So for this first one, I'm going to plug in 2x minus 1 everywhere I see m. And in the second one, I'm going to leave just the x's, but I'm going to multiply that function by 3. And so let's look at these two pieces in action. So I'm going to get 2 times 2x minus 1 squared. This is the first piece. Plus 2x minus 1 minus 1. And then I've got minus 3, and then it's just b of x, so it replaces the m's with x's. So 2x squared plus x minus 1. And so at this point, I just multiply everything out, and then I simplify the variables involved. And so I'm going to get 2, and this is going to multiply out, so it's going to be 4x squared. 2x times 1 is 2x, don't forget the negative, and then double that, so I'm going to get minus 4x, and then squaring the negative 1 gives me a positive 1. If you're confused on what steps I just did there, remember that is squaring a binomial, and that is a, in this case minus in the middle, a minus b squared is a squared minus 2ab plus the b squared. That's what gave me this result. Everything else comes out of parentheses here. I'm going to keep the brackets on for now. So continuing down, I'm going to worry about the part in green in a minute. Multiplying this out, we're going to get 8x squared minus 8x plus 1 plus the 2x minus 1 and minus 1. Combining like terms at this point, I'm going to get 8x squared. That's the only squared term all the way across. I've got a negative 8 and a positive 2x, so it's minus 6x. Plus 1 minus 1 minus 1 is going to leave me at minus the 1. Now we'll work the green part. The minus 3 will distribute in the negative 3. And so I'm going to get minus 6x squared minus 3x and plus 3. There's nothing else to simplify in the green, so I'm just going to carry down to the next two lines. And at this point, I can drop the parentheses from the blue part because there's nothing else to be done with those, the brackets that we had there. And then our last step is to combine like terms. 8x squared minus 6x squared is 2x squared. Negative 6x and negative 3x will give us a negative 9x. And negative 1 and positive 3 would be a positive 2. So there we go. That's what we've got. And so these aren't as hard as they look. You're just doing what the functions are telling you to do. We're not plugging in a number. We're plugging in a polynomial to turn these into new polynomials, basically. And this is what we call function compositions as we go along. And we'll talk more about those a little bit later this chapter. Last function we're going to look at, and then we're done for today. Find g of 2x plus 1 minus 2g of x if g of b is equal to b squared plus 3. And so I want you to pause the video for a second and just plug it in to see what you get. Don't, if you want to try it all the way out, try it all the way out. But I want you at least to try and plug this in and see what you get to write. So pause the video for a second and do that. All right, so we're going to do the two pieces. So we've got g of 2x plus 1, and so that's going to be g or not the g of, let's rephrase this. We're going to get the 2x plus 1 squared, because I'm plugging this into the b, plus the 3. That's the first piece. And again, I'm going to change colors here so you can see the first piece versus the second piece. My second piece is this, minus 2 times g of x, which means I'm just plugging in x for the b. And so I get x squared plus the 3. Again, if I had something other than just x here, I would definitely use parentheses, but a variable squared is going to be the same either way. And so let's go to the orange first. Oops, get the right color here. Squaring this, again, we're going to use a plus b squared, and so it's a squared plus 2ab plus b squared. And so 2x squared is going to be 4x squared. This times this, so 2x times 1 is 2x. Times it by the 2, we get 4x, and 1 squared is 1, plus the 3. combining like terms, and I don't need the parentheses at this point, 4x squared plus 4x plus 4. The part in blue, distribute the -2 to both, and so -2x squared minus 6, and that will come down to the next line. And then combining like terms, 4x squared minus 2x squared is 2x squared. The 4x has nothing to combine with, and then the +4 and the -6 give us a -2. So that's where we're at. Again, it's not complicated here. That's where we're going to stop for today. We'll look at the graphs tomorrow, as you can kind of see it peeking up into the next example. But we're going to look at the graphing of polynomial functions tomorrow in the second half of this lesson. So I hope you all have a great day. The word of the day is evaluate. Again, the word of the day is evaluate, and I hope you all have a great one. Bye.